A very good morning to all the respected dignitaries, respected director sir, esteemed faculty members, participants, and all my dear students. And very good morning and namaskar to our respected sir. On behalf of
Good morning, good morning.
On the behalf of Department of Electrical Engineering, it gives me immense pleasure to welcome you all for today's technical session of our STTP on recent advances in intelligent system and smart technologies for core engineering applications. On behalf of BCET, I extend a warm and heartfelt welcome to Professor Dr. S. Banerjee, sir, professor at the National Institute of Technology, Durgapur, and thank him for sparing his valuable time to share his knowledge with us. Today's session is going to be very special for us as we are privileged to have an eminent academician and researcher who will share his valuable insights on a very interesting and emerging topic. It is my great pleasure and privilege to introduce our distinguished speaker for today's session, and Dr. Banerjee. Professor Dr. Banerjee is a highly respected academician and researcher in the field of electrical engineering with extensive experience in teaching, research, and innovation. Over the years, he has made significant contribution to advanced areas of electrical engineering, particularly in the domain of electromagnetic system, control engineering, modeling and control of switch mode converters and inverters, multi-level inverters, and different modulation techniques, electromagnetic levitations, and modern electrical technologies. His research work has been widely recognized, and he has published numerous papers in reputed national and international journals and conferences. He has also been actively involved in guiding postgraduate and doctoral scholars and has contributed significantly to the development of cutting-edge research in the emerging technologies. Today, we are indeed fortunate to have Sir with us to deliver a lecture on the topic, which is electromagnetic levitation and control. Without taking much time, I would like to request Sir to kindly take over the session and enlighten us with his expert lecture. Sir, please.
Thank you for your nice introduction. Just before that, I just want to talk with Professor Ganguly, sir.
Yes, sir. Sir is
Sir
there.
is there.
Yes,
Good morning, sir. How are you? Sir, your
Sir,
you
you are
are
muted, sir. Sir, please unmute yourself.
sir. You unmute yourself.
Sir, sir, you are not audible, sir. Please unmute yourself.
Yeah. Now audible? Now audible?
Yes, sir.
Now
Yes,
it
sir.
is audible, sir.
Thank you very much.
Thank you.
Dr. Banerjee, we are so thankful to you. You are such a important person. You have become field of electrical engineering. We are
No,
very
sir, no.
happy to get you in spite of your very busy schedule. So please help our faculty, students, and everybody. They are organizing this particular program, 5 days FDP and short-term training program. So even in spite of our busy schedule, you have attended and giving your lecture. Thank you very much, Dr. Banerjee.
Thank you, sir. Actually, this is my second session, I think. 2 months back, I was there in your institution, means in online, of course. There was another FDP arranged by Madam Kamalji. Now, this is my second lecture, I think. Okay.
Thank you.
So, anyway, when she approached, and particularly from Bengal College, always, if you call me, I will be always there. So, earlier also it happens. So, I think your health is okay, sir.
Just pulling on.
Okay, sir. Thank you. Thank you. Okay, I will talk much after my deliberation. Okay. So let me share my screen.
Yeah.
Is it visible?
Yes, sir, it is visible.
Visible. Yeah.
Yes, sir.
Actually, when Kamalji told me to give a lecture on this particular topic, recent advances in intelligent system and smart technologies for core engineering applications, actually then I thought that nowadays there are many development in recent technologies in recent intelligent system in transportation system. Perhaps many of you have heard about this maglev train and hyperloop system. These are all actually recent technologies and intelligent systems. But you know, these are all applications for these electromagnetic levitations. Now, it is really difficult to demonstrate all this maglev train, though I have some module or hyperloop system, because last year, I went to IIT Madras as a jury member for Asian Hyperloop competition. Okay, so I have some model, but for the basic level, I thought that the basic foundation of electromagnetic levitation and its control, I should teach first, and then maybe in next course, I should demonstrate that hyperloop or maglev train kind of thing. Okay, so as I told you, this electromagnetic levitation is one of my research topic. Actually, some of PhD student as well as myself also worked on this electromagnetic levitation and control. It is an interesting area, multidisciplinary area. You know, first, before going to levitation, you know, what is the definition of levitation and maglev or magnetic levitation? The suspension of objects with no visible means of support due to magnetic force is termed as magnetic levitation or maglev system. In short form, it is very common, maglev. Perhaps many of you have heard this term maglev. Maglev means magnetic levitation. Now, as I told you, this when something, any conventional system, you can replace with maglev system, because if it is contactless, then it will be superior than any conventional system because of its less friction. No, virtually there is no friction. There is no noise, no. And nowadays it is very much required that clean, contamination-free environment. There is no vibration. And you can develop high speed for some applications for suppose any rotation or anything in applications like active magnetic bearing, where a very high speed is required. So conventional bearing system or any electrical machine or any machine, you can replace with this active magnetic bearing. So there is less energy consumption because there is no contact. It is non-contacting. So there are a lot of advantages. So that's why there are many applications nowadays, particularly maglev train, active magnetic bearing, hyperloop, in wind tunnel, anything in industry you can find it, anything in instrumentation, particularly biomedical instrumentation. In semiconductor industry, you know, clean environment is required. There should not be any contamination. So all these things done with electromagnetic levitation system or levitation system. Okay. So as I told you, it is also written here that modern applications of levitation in equipment like magnetic bearing, magnetically levitated vehicle that have given renewed impetus to research efforts in the direction of magnetic. So those who want to work on levitation system, you know, there are many aspects open for research and development in the maglev because it is a interdisciplinary concept. You can work in the field of magnetics, you can work in electronics, you can work in mechanical engineering, measurement and control. So there are different areas. So I think here in this FDP also, there may be many faculty members, those who want to work on the different system. So you can work on this. Still, there are different direction of work is still open. Now the classification, levitation actually, particularly magnetic levitation, it can be different ways. You can do with the DC electromagnetic levitation. You can with AC excitation system, what is called AC electromagnet. Okay, so AC, both are feasible, but particularly for high payload, when you talk about that maglev train, there we need DC electromagnetic levitation system. Of course, there are another type of levitation system which is actually based on repulsive force. You know, Japan railway system, Japan has developed electrodynamic levitation system. Okay, that levitation actually due to the induced eddy current when there is a relative motion between magnet and conducting surface. And superconducting magnet is used to generate such high fields. And Japan railway system is based on this electrodynamic levitation. But in electromagnetic levitation system, actually no such superconducting magnet is used, only electromagnet, very high rated electromagnet, and what we call other object like rail, that is used. And it can be also DC, based on DC excitation, or what we call DC AMLS in short form, or AC AMLS, particularly excited by AC electron. But you know, in AC system particularly, there are losses due to eddy current and hysteresis. So efficiency-wise, it is lesser compared to DC electromagnetic system is more efficient than AC electromagnetic levitation system. Configuration-wise, again, there are two types, stationary magnet. I am coming one by one. And in some cases, you can find that magnet itself is moving. In moving, particularly maglev train or magnetically levitated vehicle, there you find that magnet is itself moving with the platform. So electromagnetic levitation, you just see the two figure as I told you here. This is electromagnet and this is object. This is the ferromagnetic object that has to be suspended in the air under this electromagnet. So when you excite this electromagnet, okay, this object.
Excuse me, sir. Sir, your screen is not visible.
Screen is not visible.
Yes.
Let me go. Maybe it was earlier visible.
Yes, sir. Earlier it was visible.
So yeah, I can leave and then join. Okay, maybe internet issue.
Okay, sir. No problem. All please stay connected. Sir is joining us within a short while.
Now is it visible? Hello?
Yes, sir. Now it is visible, sir.
Okay.
Yes, sir.
So you see that when you excite this electromagnet, this object there will be attraction force developed between the magnet and the ferromagnetic object. And if there is no control, nothing, then this object will attach to the pole face of the magnet. And if this our gravitational force is more than the attraction force, then it will fall due to gravity. So it will be open loop unstable basically. So you have to control on it. In other case, you just see this the electromagnet is in the down, and this guideway or rail. Okay, there it is there on the up. So if we excite this electromagnet If I fix the guideway, then it will move. So you have to basically control this air gap, this gap, okay? And you have to stabilize it. Basically, it is unstable. Why it is unstable? Because you see the force of attraction between magnet and this object is directly proportional to the square of the current flowing through this coil and inversely proportional to the air gap distance square, this air gap distance. And you see the force air gap characteristics is inversely proportional. Okay? And force current characteristic is like this. It is directly square proportional. So if we see around an operating point, this is highly nonlinear system. And if we just want to linearize around an operating point, say particularly this point, and if I draw a tangent here, it will give a positive slope, but in force distance characteristics, it is giving a negative slope. Okay. And this negative slope, while go to the mathematical modeling, you can see this negative slope basically will give one right half plane pole. Okay. And you know, if there is any right half plane pole in control, basically it is a control problem, then system will be inherently unstable. Okay. So you have to stabilize. So it is open loop unstable, and this system, electromagnetic levitation system, it cannot run in open loop, and closed loop is mandatory. Okay. Because what you have to do in closed loop, you have to reverse these characteristics. Instead, like this force distance characteristics, negative slope, it should have positive slope. Means when air gap distance will decrease, your required force should decrease. Required current flow through the electromagnet should decrease. And when the air gap should increase, then your required current as well as the attraction force should increase. So instead of this negative slope, it should have been positive slope. So how can you do that? You have to do with controller as well as closed loop control with sensor and all this, amplifier, power amplifier, and controller. Okay, so there are two schemes already displayed here. One is just one single loop control using only position sensor. You have to sense this gap dynamically and fed to the controller. Controller will generate control signal to the amplifier, power amplifier. Finally, power amplifier will excite this actuator or this electromagnet depending on your required force. Okay, so this is both way it is possible, just using single loop control, or for better tight control and robust control, you need another loop internally, which is actually current loop. Okay, you just see here, we are sensing this current by current sensor. In the outer loop, you see there is a position sensor. So you have to sense this air gap distance all the time, and you fed it compared with the reference air gap. Reference air gap actually the demand at what particular position the object should levitate. Okay, so it should always follow the reference air gap. And then there is a error signal, and then this position controller. This controller basically will stabilize the system. Okay, the unstable system will stabilize by this position controller. Then it will generate this reference current. Actual current is sensed by current sensor and compare, and then fed to the current controller. And this will generate the control signal, which will modulate the PWM pulses for DC to DC power amplifier, which actually will control this electromagnet current as per your requirement. Hope this control philosophy is understood. If you have any query, you can ask me. because this is the basic fundamental about the electromagnetic levitation system. Now there are, you see, there are different components. Particularly electromagnet is mandatory, and another object, the suspended object, in case of any other application, it should be ferromagnetic type object, because that should develop the attraction force between magnet and this ferromagnetic object. In a railway system, you see, this is guideway or rail. Okay, this may be other way. You can also have inverted electromagnet, or the body can be off and the rail can be in the down in the normal railway system. Okay, it can be both way. Position sensor, that is mandatory. You should have power amplifier, power electronics. So that is applications of power electronic instrumentation. Control system, the control, you have understood about that in basic control, like classical PID controller, lead lag controller. These are all applicable if you go through a linearized model. If you think about that nonlinear model, then highly other advanced controller like sliding mode controller, feedback linearizing controller, that fuzzy controller, that all also will also be applicable. Okay. So the characteristics of DC electromagnetic system, as I told you, this is open loop unstable system. So this is a basically open control problem. It is highly nonlinear. It is highly nonlinear, not because of these characteristics, because of these magnetics also. You know, eddy current, hysteresis is also contribute to the nonlinearity. The parameters of the DC electromagnetic system will change with the air gap position. You know, with the change of air gap position, these characteristics of this magnetic system will change. And as control engineer, you have to design robust controller, even though the parameters of the electromagnetic system will get changed. And you know, the time constant of electromagnet, particularly for highly rated magnet, the inductance L by R ratio is the time constant. Okay, so you have very large time constant. So you have to design power amplifier to take care about this time constant. Otherwise, it will be very slower power. Okay, you have to be fast enough to control the such type of L by R high time constant electromagnet. And generation of electromagnetic noise, that you know, EMI, is a common issue in case of electromagnet, and that also you have to compensate. Otherwise, it will create problem in the sensing devices, particularly for
Sir,
position.
excuse me, sir. Sir, Sir, your screen is not visible. Sir, you have clicked on stop sharing. That is why.
Stop sharing? No, I am always, it is share only.
By mistake, you had clicked.
Okay. It is again?
Yes, sir.
Sharing?
Yes, sir. Yes.
Oh, this signal. Okay. Take care.
So at the bottom, no, there is.
No, now it has.
By mistake, it was clicked.
Okay. As
Yes,
I told you, that there are different components. So electromagnet is the major component, and you know what we call actuator. This actuator you have to design. Now I am not going to the details. This is all. This is actually one of the major research, that how to design the actuator, electromagnet, as well as the rail. Okay. So for a large rated actuator, you must go through some magnetic analysis or FEM analysis using ANSYS or different software. Okay. So there are different, you just see here the structure. There are different structure here only. I have shown 6 different structure. the U-core, E-core magnet with different coil structure, and you see the guide way, it may be flat, it may be projected, like this. And for one analysis, I have just go through this ANSYS simulation model, and you can see with this how flux will vary, okay? This flux pattern, as well as you see the field intensity, how it will vary. And you see here, the field intensity is maximum in the air gap, okay? And how it will distribute it, how it will optimize that structure, that all depends on this flux density, field intensity, and how the force develop. Okay, these are all the vector plot of force for different structure, UI structure, U structure, and I have shown the plot, the force versus air gap, flux density, all will vary with the air gap, particularly it will decrease. If we increase the air gap, it is very much common that if we increase the air gap, then your force between the electromagnet and the object will decrease. But objective here to show at a particular operating point, which particular combination will generate the maximum force or the maximum flux density. Here you see this structure, okay, particularly that UI structure with upper coil, means UI structure with the upper coil, it will generate the maximum force, and it will be helpful for selection of this structure, how much force is required for a particular payload. Okay, that is decided initially by this software analysis using ANSYS, Maxwell, or any kind of FEM analysis. Okay, so for the same dimension of electromagnet and rail, the lift force developed between the UI structure is more than U or EI structure under any operating condition. Now come to the power amplifier. It is another important component in case of electromagnet, because you know the coil current is to be precisely controlled to meet this attractive force demand, and this calls for a fast DC-DC power amplifier. Basically, in DC electromagnetic system, you know, the input is DC, so output also is DC, but it should be a variable DC. You cannot give a fixed DC to the electromagnet, okay, because you have to vary this one, and for that you need DC-DC power amplifier. And here, of course, both linear and switch mode power amplifier is used, but if you go to the linear mode of amplifier, you know the problem. Their efficiency is much reduced than the switch mode power amplifier. So the characteristics of power amplifier, you should have fast dynamics.
Morning, sir.
It should be energy efficient. It should be able to handle large payload, okay, and it should have better reliability and more cost effective. Here there are different kind of diagrams, you know, power amplifier is given. This is the basic schematic of linear power amplifier, where you see this supply transformer is there inbuilt with this power amplifier. So it will have a high, it will take large size and weight, okay, and this switch, this transistor will work in active region. So though the control is very simple, but here energy efficiency is not more than 40 to 60%. It will vary within this range. But if you want to go for beyond this range, and particularly for high power handling capability, you must use switch mode power amplifier. Perhaps you have an idea, so I am not going to details about that, what is switch mode power amplifier and all. But I can show you, this is the simple buck type chopper. But problem of this buck type chopper for particularly this electromagnetic levitation system is that when the switch is on, say, think about this is electromagnet, okay? So it will be excited, it will be charging, But when the switch is off, it should prevail through this diode. Okay. But there is no negative supply. In case of electromagnetic levitation system, the coil should get positive, equal positive as well as negative voltage. Otherwise, this magnet will get saturated. So that's why this type of power amplifier means when these two switches are on, you can see this is full positive voltage is applied. And when these two switches are on, then full negative voltage will apply. So this way, your coil will get full positive as well as negative voltage, and quick demagnetization is possible, and there will be fast control using this full bridge circuit. And full bridge circuit, of course, is not the best choice in terms of cost and reliability, because here all four quadrant mode of operation is possible, but for electromagnetic levitation system, only two mode of operation is sufficient, because here both the voltage as well as current is bidirectional. But in case of electromagnetic levitation system, this asymmetrical bridge means two switches are replaced by two diodes, and when these two switches are on, you see the equal voltage, this positive voltage is applied across this coil, and when these two switches are off, these two diodes will contact. So current flowing through this coil in the same direction, because there is no need for reversal of current flowing through this coil. But what we need, that negative, when these two diodes will contact, you see the applied voltage here, it will be negative and this will be positive. So this effectively will demagnetize this coil. Okay. So asymmetrical bridge converter, that's why it is very ideal for high power levitation system. So these are all voltage and current for a particular setup. Okay, how coil current and coil voltage with gap pulse will vary. So I am not going to in details. Now this is single switch base converter. This is another topology which is used for lower payload system. Okay, so when this switch is on, you see this coil will get full supply voltage, but when this switch is off, this diode will conduct and this coil will de-energize and this capacitor will be charging. Okay, that means when the switch is on, capacitor was discharging through this resistor. Okay, and when the switch is off, the coil, this capacitor voltage effectively will come across the coil. So if we can design such way this resistor capacitor combination so that you can have equal amount of voltage, okay, positive negative voltage applied during switch off period of this device MOSFET, then there will be no chance of saturation of the magnet. So this way you can find out that requirement only of one switch and number of components are less, but of course this is not that much energy efficient like asymmetrical H-bridge converter. Okay, so this is once again coil voltage, capacitor, coil voltage, coil current during one stable levitation system. You can see how it will vary. So you need multiple coil for levitation of a platform, particularly when a platform having 4 number of magnets. I will come to different setup, you can see, follow. There you should energize all different coil by different power amplifier. So for such power amplifier using asymmetrical bridge, structure is like this. But if you can replace with the single switch base converter, so similar same capacitor and resistor, what we call the dump capacitor and resistor, and there are 4 coils. Okay, using just having this first recovery diode, you can connect it like this. Okay, a number of components will be reducing. But of course, this is not used for high power levitated system. But this is asymmetrically used bridge converter, which is more energy efficient, and you may connect so many converter in parallel, so many devices are in parallel for better power handling capability. for high power applications like hyperloop or maglev system or active magnetic bearing system. Okay, this is now the comparison of different type of topologies. So I am not going in details. Okay, here you see just that asymmetrical edge bridge converter that is written most energy efficient and suitable for high power applications. But of course, more number of components required than single switch based chopper. Single switch based converter is suitable for low power applications, but it is not energy efficient. Term capacitor resistor is required, and this resistor is a lossy system, so not so energy efficient. And of course, in terms of response, dynamic response, that study also done in a separate work. There you can see that half bridge and full bridge topology is more dynamically faster. It will exhibit faster dynamics and with a lower ripple current. Now you see another important component is position sensor, because it must be non-conductile and there should not be any contact between this electromagnet and this ferromagnetic object. Okay, and at the same time, the sensor requirement. Yeah. Is there any question? The bandwidth of the sensor should exceed the amplifier and actuator system bandwidth. Sensor should have maintained the linearity with the input gap over the range, and sensor should have the immunity from the stray magnetic field. And of course, resolution should be very high. There are different type of sensor, Either it may be capacitive type, Hall effect type, optical sensor, eddy current sensor, laser sensor. Please mute your mic. Hello? Some sound is coming.
Hello? Please mute yourself.
So there are
Yes, sir.
there are different kind of sensor. It is available in the market. You can use for levitation system, but what I have seen that eddy current type sensor is mostly used in some cases for small prototype optical sensor, because it is less cost. It involves less cost, more cost effective. That's why for smaller system, optical probe are used. But for measuring large distance, okay, particularly for applications of maglev trade, you can find the ultrasonic sensor or laser sensor used. Okay, so it is a comparative table between the different sensor. Okay, so we can also use for a particular levitation system using different sensor, and you can see their relative advantages, how much frequency response, what about the resolution, how much size and better that accuracy, linearity. Okay, all things, all studies you can do with different sensor. And it has been found that eddy current type sensor, I have also used my different applications, both eddy current type as well as optical sensor. Okay, for smaller prototype, it is very fast effective and cost effective. Okay, so there are different study. It is available in the literature also. You can use based on your suitability of application. So as I told you, among different applications, the eddy current type is mostly used for magnetic suspended applications, because this is having excellent frequency response with very little phase shift, and linearity is also good. And of course, there are sometimes it is corrupted by this high frequency switching power amplifier, because that is the problem of switch mode power amplifier. When you use the switch mode power amplifier, the high frequency related switching frequency, suppose you are operating switching power amplifier, say 100 kilohertz, so this 100 kilohertz switching noise will be there. So that you have to take care by filtering circuit. So proper conditioning of filtering as well as conditioning circuit, you can use this type of position sensor. There are also current sensors. These current sensors are of course standard, and it is used by, say, LMA current sensor, Hall effect sensor. It is having so many advantages like excellent accuracy, very good linearity, and all these things. So LA55P is a standard current sensor. Okay, so those who have worked with this, you can easily know. Then controller. The primary task of this controller is, to generate the actuating control current as per the control requirement, control algorithm. So selection of controller, as I told you, that if you want to go through in your lab scale module, based on the linearized model, linear controller like PID, lead lag, lead plus PI, there are different type of linear controller used. Otherwise, for large scale applications, you can go through nonlinear control like sliding mode control, fuzzy control, and all this feedback linearizing control. Some kind of modern control like state feedback control using state space approach, and all there you can see there are variety of controller design, and you can apply. Ultimately, your system should be stable. So this is one kind of this block diagram. Okay, here you see this is the MATLAB system plan. This is the processor plan, and as I told you earlier also, that there should have inner current loop as well as outer position loop. So here, how can you design this current control loop? That I am not going in details because I cannot cover then only 15 minutes time, I think is left. So it is all about control. If you need anything more, you can approach me. I can tell you about the design of current control. How can you plot this? How can you verify with Bode plot, frequency response? After designing current control, you design position controller, because current controller is more faster than position controller, at least 10 times faster. So that is the approach. First you design current control, then you simplify as it is a simple gain block, and you design this position control based on this. So you see here this electromagnetic levitation system in the S plane. There are two poles, one at negative and another is right up, equidistant right up. So suppose this is 38.15 and this is 38.15 positive. Because of this pole, okay, the system is unstable. So that's why you have to stabilize with this lead controller with this, okay, and it has been stabilized by this response. You see there are different air gap position. Lead lag controller has been designed, and PID controller is designed for different gaps. And this is once again another controller, lead with PI controller, and there is a comparative study. You see how it will perform based on the similar operating condition. But you find it that this type of MATLAB levitation system, here you need this kind of response. So there you did not have this much overshoot or this much steady state error. So be careful about the selection and design of controller, so that at the same time there should be a faster response as well as no overshoot and no steady state error. Okay, so this is the mathematical modeling as I told you. This is the distance between distance and inductance characteristics, gap distance and pickup current characteristic. These are the two important parameter while finding the magnetic the model. Okay, so as you see that at the lower gap, the inductance is very high. At the same time, at higher gap, the larger requirement of current is very high. So you have to optimize about the selection of operating point. Okay, and it is found that this medium zone is suitable for selection of operating air gap. So based on these assumptions, you can go through the modeling part, okay? And there are different modelings here. One approach is given. You see based on this linearized equation, inductance and force equation, you can linearize it about an operating point and using perturbation technique, or you can go through the Taylor function expansion, and you can see this is the model. Here you see that output position to current. That means if it is excited by control current source, then you see in the denominator this S plus root over this KZ. So one of the pole will lie on the right of S plane. And this is coming because of this negative slope characteristics. Okay. And if I go to the perturbation in the voltage equation also, so you can see that this is a third order unstable system. Okay. So here also one of the pole is lying on the right of S plane. So this is one setup where you see this is the electromagnet of the lab prototype, and this is the rail. So you have to suspend this thing under this rail by using the position sensor and other circuitry. So I am not going to details. I just want to show some demonstration. This is about the controller design. So all things are there as per linear control here only. Okay, so when you can stabilize, you see that at this zone from the root locus, system is stable, and after having some gain, the roots are going on the right of S plane and system become unstable. So these are the parameters for one stable condition. Okay, so these are the hardware circuit. You know, either you have to go through analog control or digital control for designing all this controller, PID or bit lag, all this controller. So this is the setup. You can see this this is actually single axis levitation, because this type of system you need multi-axis control. Only single axis levitation it is shown that it is floating under this electromagnet. Okay, under this condition you have variation of different distance at this air gap, as well as variation of different input link at this change of mass. So to show this how your system maintains the robust stability with the change of parameters. Okay. So these are all, this is one setup where you see this cylinder is levitated under this I-cord type magnet. You have to sense this by the air gap by this position sensor. Okay, and the structure of this in this case is like this. So here also I am not going in details. So these are the demonstration of position and current responses. Okay, so these are mandatory because it is not only question of stability, but how robustly it will perform, and that only can be verified by giving some disturbances. Okay, starting from that when main switch is on and off, and you can see how it will perform. Here you see the two actuator based levitation system. This whole cylindrical rod can be levitated under two coil levitation system. Now it is a multi-coil system. Okay, and multi-axis levitation system is possible using, so two coil. So there are two power amplifier. Okay, so two sensor. Now you see how this cylindrical rod is levitated under the two coil system. Okay, it is completely floating, and this is done in our laboratory only. And you see this is tilting condition. You can control this position by changing the reference in one side. It is just demonstrating that how can you levitate this complete ball in other direction. Because of that, in some applications, in one side you need more ports, another side, particularly in the induction furnace and all kind of applications, you see there it is possible by multi-coil system. And these are all experimental results. I am not going to in details. Okay, this is now a platform-based levitation system where four coils we have placed in the levitated platform. You see here, and how the position sensor is sensing all coils. Okay, and this, you see this, it is lifting from this platform from that ground. Okay, under this levitation system. Here four magnets you have to control independently by four different power amplifier, four different sensor, four different current sensor. Actually there will be four loops, and if you want to control better, then one master controller you should use. Okay, so that also can be done with either analog control or digital control. Here, of course, since the prototype is having only 20 kg weight, so I have used this single switch base convert the power amplifier. Okay, then structure of this power amplifier is like this. So here you see how object is levitating under stable condition. Okay, here in this case and this case. So practically this type of platform is the concept, basic fundamental concept of levitated vehicle. See, if you have a levitated train, then initial job is this kind of levitation, and then there will be propulsion, and this propulsion is a separate subject. Actually, it is done by either linear induction motor based on switching, okay, or linear synchronous motor also possible. Okay, so these are the experimental results. It is in stable condition how this position signal, only slow vibration is there, it will be there only, but it will not be much more compared to the DC signal. Okay, and how see the noise signal, this actual position signal is this one, and how it is filtered out. Okay, this filtered out signal is there by means of filtering, because otherwise your system will not work. And particularly here you see there is no noise. Okay, so you have filtered out and signal conditioned by conditioning circuit. So all these applications of instrumentation as well as electronics, power electronics for power electronics engineer, machine for machine design, and that actuator design. Okay, so it is hardcore your engineering, core engineering. And these are of course the different current signal, position signal in a different channel. Particularly you have to use that multi-channel oscilloscope like Yakogawa. I have used this one. Okay, here you can see all signals at a time. So how signals are matching, tracking with one after another, you can see here. Okay, this you should demonstrate. When you go for research or making a paper, you have to establish this kind of logic, otherwise your viewer will not accept your paper. Okay, so these are all experimental results. I am not going in details. And you see here on lab scale module made by feedback instrument that how this ball is completely levitated using this prototype here. This optical sensor is used. One side is LED, another side is phototransistor. And the principle is that when the object cuts, and there the signal, the signal will go to the controller. Here both analog as well as digital controller is there. A computer-based control is there, and I will demonstrate also. I will show at the end the video how it will be stabilized with the different control. And this control you can design. One of our students who is presently working in BC Engineering College, Dr. Soham De, has worked on this setup with different controller. Even fractional order controller is also used for this setup. So I am not going to in details because their time is also up. Okay, here you can also see that if you want to use this simplified linear controller, then your zone of operation is restricted. So here is one setup where you can use switching controller based on the air gap position. You can switch. There are different bank controller. This is for say low gap. This controller is for medium gap, and this controller is for higher gap. And there is a switching logic based on completely analog principle. You can also use for digital very easily. Okay, and then you can switch on controller so that your levitated object will maintain stability even though there is a change of air gap position. And this way you can extend the operating air gap. Okay, so these are all published literature. You can see all of my work in the standard journal like IEEE, IET, okay, Elsevier journal. There are many publications, so you can easily find out. You can also use the performance with different model control like model matching control. Here you see whatever reference you can give, your output will vary as per this reference, because this is very much required, this type of response, particularly this type of critical system, as I told you, where there will be no overshoot, no steady state error, and at the same time it will be critically damped response. So this type of practical response is also done with a particular setup using model matching control. So these are all like advanced as well as model control used for different setup, okay? And these are all experimental results, how that output position will vary with a triangular wave as well as sine wave, okay? And you can extend the range of operation. And here it is one setup. You see that completely it is done with dispersed setup. One of my students has worked, who is now presently at NIT Jamshedpur, Dr. Minal Kanti Sarkar. He has worked on this setup. And here you see the different position sensor, electromagnet power converter, signal conditioning circuit, and using digital platform disperse is used for this system. Okay. So this is all about this my presentation. Now you can see that particular video for this MagLab setup. So here you see this MagLab ball with the disturbance, how it is floating with the controller, okay? And so this control is done by fully computerized system, and how it is tracking with the performance. Sinusoidal disturbance is given and it is completely tracking with the system. So this is another tracking system with a square wave input. You see that how it is matching. Okay. So if there are any question, because I have another meeting. Hello.
Hello. Yes, sir.
So,
Any question? Any question from the participants, students? Any question? Sir, I have two questions to ask.
yes, please.
Sir, so I want to ask first question. What is the importance of air gap control in the MagLab?
Yes, air gap. See, if you let me go for this. Can you see this slide?
Yes, sir. Yes, sir.
I should go for this. Air gap. This is the air gap. Okay.
Yes, sir.
If this air gap is too small,
yes, sir.
If this air gap is very small, then you see these characteristics, as I told you earlier, that inductance is very high. Okay. And there is also chance of accident, particularly for say MagLab trend-like applications. So it should not be very small. Right?
Yes, sir.
It should not be very small. At the same time, if we go for very large air gap, then the problem with sensing by means of position sensor, as well as you see at the very high gap, the required current is very high. If required current is very high, means you have to enhance the rating of power amplifier. Okay, so you have to optimize.
Yes,
you have to optimize. You should not use very small gap as well as very high gap. So what we have, the preferred zone of operation is the medium gap. Medium gap means, suppose say a particular position sensor measures say between 0 to 20 millimeter. Okay, then 10 millimeter you select, and you can vary within 15 to say 5. 5 to 15 will be the variation. Then it's fine.
Yes, sir. Understood.
Got my point?
Yes, sir. Sir, another question. What are the challenges in designing the MagLab for industrial application?
Yes, challenges of design of maglev in industrial applications. Actually, as I told you, this is first thing is unstable system.
Yes, sir.
Particularly if you work on this electromagnetic levitation. Why it is unstable, I told you, because of these characteristics.
Yes.
Okay, you just simply follow the electrical principle. Here, what this air gap? When this air gap is reduced, okay, the force, required force between actuator and position of this object should be smaller. But this is the invariant property. This equation is coming from Coulomb's law, you know. Coulomb's law. If you have a two charged particle, Q1 and having charge Q1 and Q2, having a distance between them Z, then it will be Q1 Q into multiplied Q2 by Z square. Okay.
Yes.
So the required inherently it is required. It is having a high force. But you see in real life applications, it should have been reversed. It should have been reversed. Means when distance is small, your required current should be small as well as required force should be small. And when the air gap distance is large, your required current should be higher.
Yes.
Okay, but practically this is the invariant property. That's why it is having a negative slope.
Yes.
And because of this negative slope, you are having one of the pole lie on the right of a spin. If you, without going through details about modeling, if you just write the fundamental equation and go through the Taylor series expansion, you see that how it is affected in stability.
Yes.
It will always have one of the pole on the right of a spin because it is giving positive slope, but it is giving negative slope. Yeah, am I clear?
Yes, sir.
So this is the first thing that what I call you that it is unstable system. This is one of the challenging problem. Another challenging problem is this is highly nonlinear. Okay, highly nonlinear because not because of this only this characteristic. You see, this characteristic is highly nonlinear. You are also using the electromagnet, which is producing the eddy current losses, hysteresis, saturation problem.
Yes.
So you have to demagnetize quickly the magnet. For that, you need faster and efficient power electronics amplifier that I have also explained. Which power amplifier will produce equal positive voltage, positive voltage as well as negative voltage, so that your electromagnet will not be saturated. This is another issue. Your position sensor you have to select so that position sensor will not be corrupted by this high frequency signal noise. Okay, you have to filter out then. Okay, so these are all problems, and these all problems are written here only. It is open loop unstable, it is strongly nonlinear. The parameters will vary with the air gap changes because inductance is changing with the air gap change. Your required current is changing. And if you go for the high power application, particularly for industry, then you have to use large magnet. There, the time constant of the magnet, L by R, because
Should be
ultimately
very
if you
high.
go to the current, is very high.
Yes.
Okay. So particularly current, you know, in the current loop you see, if we go for current loop here, better I can tell you here, if you go for this particular current loop, here this magnet is there. So this current controller particularly will take care about this magnet time constant. So this power amplifier should be fast enough to take care of this large time constant. Okay, this is another issue. So these are all issues, like, okay.
Yes, sir. Yes. Understood, sir.
Any question?
Any question from anyone, please? I guess there is no question.
Okay,
So,
if there is no question, then you can
sir, I want
you
to
can
conclude.
also send me if you have any query, particularly if you work on this. Then This is
Okay.
basically interdisciplinary, multidisciplinary subject.
Yes, sir. Yes, sir.
Okay, in electrical engineering, also you can see there are many applications of this electromagnet design, then use of sensor, use of power electronics amplifier, fabrication control, then this analog, digital, or signal processing. All things are applicable here.
Yes, sir.
Okay.
So I guess there is no question. Now I want to conclude. I would like to express my sincere and heartfelt gratitude to our esteemed speaker, Professor Dr. S. Banerjee sir, Professor from NIT Durgapur, for delivering such an enlightening and informative session on electromagnetic levitation and control. Sir, your valuable insights, clear explanation, and depth of knowledge have greatly enriched our understanding of this advanced and emerging area of engineering. We are truly grateful for you, sir, for sparing your valuable time and sharing your expertise with all the participants of this STTP program. I would also like to thank all the participants, students, for the active participation and interest, which made today's session truly interactive and meaningful. Once again, I want to thank you, sir. Thank you so much.
Thank you. Okay. Welcome.
Okay. With this, I want to conclude. Thank you.
Okay. May I leave now?
Yes, sir. Yes, sir.
Thank you very much.
Thank you, sir.